you try to speak, I won't be able to hear you. If you do want to ask a question, feel free to unmute your mic or just sort of raise your hand, and whichever way works best for you. We mute them because if there's any background noise, it makes it difficult for everyone else to hear, and this just is more efficacious, we've seen from doing this for quite a while. So today's webinar is Dollars and Cents, the ins and outs of life cycle costing with GLD, the ground loop design software. And really, just as a preview of the other webinars we have in this series, we'd be thrilled to have you attend more of them if you're interested. Next month is called Effective Energy Modeling. We're going to have an expert in energy modeling coming on to talk about energy modeling and geothermal. And then in July, we're going to have a class on thermal conductivity, thermal response testing. In August, we're going to discuss improved communication strategies for basically just discussions between engineers and drillers. And in September, we have what's really interesting. We have a climate scientist coming in talking about geothermal technologies and the relationship to climate change in the upcoming years and decades. And then in October, we have a section called Educating Geothermal Operators. These are the series classes that we have listed. So feel free to join others if you want. So this presentation today has 4 parts. First, we're going to start with what is life cycle costing, because I'm sure some of you know all about it and some of you may not. So I'm just going to start with some basics, then grow from there. Then we're going to look at what is the GSA module, it's Ground Geothermal System Analyzer module. Then we'll look at the standard inputs for life cycle analysis in this module. And then we'll really just start playing with it and do a couple of samples. So what is life cycle costing? So I got this off of Harvard's website. They do a life cycle costing for all their buildings. Life cycle costing is a method of economic analysis for all costs related to building, operating, and maintaining a project over a defined period of time, say 10 years, 20 years, 30 years, etc. Assumed escalation rates or inflation rates are used to account for increases in utility costs over time, such as maybe electricity is expected to go up 5% per year, for example. Future costs, meaning like maintenance costs 5 years from now, or energy costs 5 years from now, et cetera, are expressed in present-day dollars by applying what's known as a discount rate, which is a critical variable. All costs and savings can then be directly compared, and fully informed decisions can be made. So one of the key variables here is the discount rate, and it's slightly abstract. So let's start looking at this now, because it is sort of the heart of the analysis method. So the basic discount equation is as follows. On the left, we see the present value of something. This could be the present value of a candy bar, or the present value of 20 years of operations of a geothermal system. The present value equals the future value, which we see circled, over 1 plus the discount rate, or where the discount rate is kind of an inflation rate, raised to the y power, or y is number of years into the future. So if we wanted to say, okay, 20 years from now, I know my operating cost for electricity is going to be $10,000. You put $10,000 in the numerator, and you have 1 plus your discount rate. Let's say it's 5% per year, so it'd be 1 plus 0.05. Then you'd raise it to whatever, 10 or 20 years. And then that calculation on the right will give you the present value today of that future operation cost. This is sort of the fundamental heart of life cycle costing. So let's look, how do we determine future values here? For geothermal and for any simulation or analysis, it's kind of complicated. So the cost here in year Y, which is in the future, some point in the future, is going to equal, for example, the cost this year times 1 plus the escalation rate raised to the Y power, meaning Y meaning years from the future. So let's say we're interested in the operational cost of, just say, electricity for a geothermal system in year 20, as an example. So we'd say, okay, if the first year's cost would be, say, $10,000, then we have 1 plus the escalation rate, say 5%, raised to the Y power. It's just a variation on the discount calculation, but this is what we use to help figure out future costs. And then to sort of bring everything together into a life cycle cost analysis, we see that the life cycle cost here is equal to basically your upfront capital costs, your construction costs, your loop field installation, mechanical systems, et cetera, plus the present value that we've calculated for recurring operational expenses, electricity maintenance costs, water costs, whatever. And then you can subtract out the present value of residual value. So if you do a 20-year life cycle cost, and in year 20, you say, what's the residual value of my loop field in year 20? Kind of like a salvage value. And we figure out what the present value is of that as well, using those equations that we just looked at. So that's the basic of life cycle costing. This is meant to be merely an introduction, certainly no substitute for a full class on it, but just to make sure everyone's kind of on the same page on what the generals are of life cycle costing. And this is an example of a life cycle cost analysis in the GSA, or Geothermal System Analyzer module. So I've just received a message that they asked me to speak a little louder. Jeff, is that still an issue, or can you hear me okay now?
A little bit more would be helpful.
Okay, I have the mic right by my ear, but sure, I can tone it up a bit. Okay, great. So so this is a sample life cycle analysis. We see the life cycle tab here, and we see variable costs, things that change from year to year. We have fixed costs, things that are just like one-time costs. Then we have a geothermal column here, and we have a conventional system that we've defined as an air-cooled chiller and a boiler. We can see over 30 years, we see the energy costs, CO2 emissions in terms of tons and dollar amounts, water usage, maintenance costs, the value of the mechanical room space. These are our variable costs. And we have our fixed costs, which include our installation at the subsurface level, our equipment, our heat pump equipment installation costs, our controls costs. We have tax credits, depreciation. Anything in parentheses is a minus, meaning it's subtracted from like the net present value or cost analysis. So anything in parentheses is a minus. We have equipment replacement costs because we've done a 30-year simulation here, and at some point in time in the future, the mechanical system wears out, so we model that. And then we have salvage value, which is, what's the value of that mechanical system 30 years out? What's the value of that pipe in the ground after 30 years? And we see that life cycle total is $1.3 million in this example for geothermal, and $1.8 million for conventional. So this particular system, the net present value of installing it's $500,000 positive, meaning whoever's going to operate the system is looking at $500,000 in savings. So in summary, life cycle costing is a standard investment analysis method that counts present and future costs and savings and converts them in today's dollars terms. This is known as net present value, or NPV analysis. Future costs and savings are converted in today's dollar terms using the discount rate. Typically, the commercial real estate sector likes to see NPV analysis that has an investment payback of approximately 8 years or less. Institutional sectors are more flexible. To do a full net present value analysis on a geothermal system requires the designer to take into account hard and soft costs, which we'll look at in a moment, for a geothermal system in one or more conventional systems. To do the analysis, we need to compare something against something else. So what is the GSA module? What is this tool that enables us to do this? The Geothermal System Analyzer, or GSA module, enables customized, quick, and accurate life cycle costing specifically for geothermal systems and the unique and valuable benefits that they provide. We basically got a lot of feedback from our customer base over the years telling us exactly what they wanted to see in this module. So the things that are in here are based on what our customers wanted to use it for, in their daily work. We didn't just sort of make this stuff up. And by meaning make up, I mean the different lines. The net present value or life cycle analysis is industry standard. But, the content, like some of our clients said, my geothermal project saves my client maintenance costs. Put that in there. Like, of course we'll put that in there. Or my geothermal system is a smaller square footage footprint. How do I account for that savings and show it to the client? So we put mechanical room lease in there. So these are the different variables and where they came from. And so this is another screenshot of the life cycle costs, or GSA module. We have the life cycle tab here. Here we have another tab here, analysis tab, which kind of is a summary of your life cycle cost analysis. We can see annual savings for this particular system, net present value savings, CO2 reductions per annum and over 20 years. Then we have different sorts of paybacks, simple paybacks, internal rate of returns, and then RHI values. RHI is renewable heat incentive, something that started in the UK and now is slowly working its way into North America as well. Now, what are the standard inputs for life cycle analysis? If some of you have never done life cycle analysis, you may be surprised by the range of things you have to basically take into account to do an accurate and detailed life cycle cost analysis. Now, there's no requirement to use these all. If there's certain things you don't know about or don't care about, you can ignore it, and inside the GSA module, it'll ignore it as well. but we're going to go through everything so that you know what's available in the tool to help you with your work. So first off, we have hard costs. These are the things that people normally think of when they're thinking of life cycle analysis. So what we need is loads and efficiencies. We need the total heating and cooling BTUs or kilowatts per system. Then we need the average equipment performance, like average COP and EER values. A lot of times people get a little confused about which COP or EER values to use. A lot of times, a lot of simpler software tools out there only give you one value. It's kind of like your design day predicted COP and EER. But you don't really want to use those values because that's kind of your worst case scenario analysis. What you want to do is calculate the average geothermal COP and EER values. This requires really a monthly or hourly loads data, dynamic pump data, and advanced loop field simulations. These simulations give you the ability to predict what the average performance is going to be over the course of the year. Like we can see this graph here, the sort of the pinkish purple line shows us our minimum entering water temperatures over the course of 10 years. The yellow ones here gives us our maximum temperatures over 10 years. And then we have this sort of hard to see pink line, which is our predicted basically kilowatt hour consumption for each month of the year, or month over many years. So this is the kind of data that we really like to see to fine-tune our COP and EER analysis to really show the most benefit that geothermal can provide. Another hard cost is our building construction costs. If this is a new building, maybe cost per square foot for construction, maybe it's $160 per square foot. We want to know what that is because if we're factoring in the size of the mechanical room, we need to know how much it costs to build a mechanical room. And then if it's an existing building, it's useful to know the value per square foot for existing buildings because of the lease value, et cetera, of that space that's occupied by different mechanical systems. Now, the standard installation costs for geothermal would be subsurface costs, and typically we measure this in cost per foot of installed pipe, like vertical foot, 12 bucks a foot, 15 bucks per foot, et cetera, et cetera. We have our equipment costs. This is typically used in the cost per square foot of conditioned space. So maybe you have a 50,000 square foot building, and I think the geothermal equipment will be $12 per square foot, for example. And then we have our controls cost per square foot of conditioned space. And so on the installation cost side, this is a chart that's been floating around the industry for a while. One big heat pump company collected this data, I think, from some of their clients. And you can just see this is the cost per square foot installed for different sorts of systems. Geothermal vertical, geothermal horizontal, et cetera, et cetera, et cetera. This is an example of kind of the format these data need to be in. Another hard cost is basically the replacement cost for the mechanical equipment. We need to factor in the time frame. How many years are we going to be modeling for? How long? What's the life expectancy of the equipment? Then we have to look at future equipment costs. What do we think the equipment costs are going to be, 15 years from now or 23 years from now when the equipment needs to be replaced? And then future labor costs, because we can anticipate, assuming it's not all done by robots, that with inflation and everything, labor costs will be higher in the future than they are today. And so here's just from ASHRAE, a list of equipment service lives for different sorts of equipment. These data are not superb, as we all know, but it's the best that we have. The control costs are another hard cost that we can consider. They typically range from anywhere from as low as 10 cents to $1.50 per square foot of the conditioned space. Really simple, well-designed geothermal systems typically have very low control costs. If you have a very complex system, that could go up higher. And again, if you have no idea what the control costs are going to be while you're doing your analysis, especially in the early stages, just zero them out and ignore them. This is a very flexible analysis method. You can choose to include what you want to include and choose to exclude what you don't want to include. Now, another hard cost, of course, is our energy consumption costs. This factors in different sorts of fuel types, current prices, and fuel inflation rates. So we see we have different sorts of energy sources: electricity, fuel oil, natural gas, propane, et cetera, et cetera, et cetera. And then there's a cost per unit here. And then down here we have inflation rates. Like here we see natural gas. We predict the inflation rate will be 4%. We could change the electricity inflation rate, et cetera, et cetera. We talked about maintenance costs in the previous slide, and here's where you can actually factor in maintenance cost inflation rates, mainly on the the labor front, et cetera. We'll come back to this discount rate in a moment. Now, maintenance costs typically for geothermal are quite low compared to most conventional systems, and it's a big advantage that I think is very important to include in your analysis. And this is just some data that's been collected through the industry over the years for a cost per square foot per year. Maintenance costs typically increase over time, just as unfortunately everything increases over time. And again, we account for this with our maintenance cost inflation rate. Now, another hard cost that's worth considering, and I think is usually ignored, is water consumption costs. This is if you're comparing a closed-loop geothermal system with, say, a system that has a cooling tower, it's worthwhile thinking about water. So say a 300-ton system is going to use about 600 gallons per hour for cooling, and water will cost maybe $2.50 per hour in that situation today. So think about it, in the future, in drought-prone regions, say like Las Vegas, for example, if climate change predictions come as they're anticipated to, and the water supply is really going to drop 30–40%, X years in the future, what do you think the price of water is going to do? How long is that system going to be in operation? It's just worth thinking about water consumption costs if you're comparing a geothermal system with a system that's going to be evaporatively cooling water into the atmosphere. Now, a soft cost is this. It's because a lot of people don't think of it as being something to include in the life cycle analysis, and in some cases it's not appropriate. Some cases it is. Now, a mechanical room is an expensive piece of mechanical rooms are expensive to build on a $1 per square foot basis. If you think it's 160 bucks a square foot, you're going to be building a 1,000 square foot mechanical room. That's $160,000, for example. If it's a new construction project, the geothermal system may require a smaller footprint and save money. For example, a classic example is a school. Let's say the school is choosing between a central plant and a distributed geothermal system. If there's a central plant, maybe they'll need 1,000 or 1,500 square feet for holding that boiler chiller system or whatever they're going to use. If it's a distributed geothermal system, maybe each classroom has a heat pump in it and it's just connected directly to its local loop field. In that case, you wouldn't need the central plant. You don't have to build it. You've just saved $160,000 in construction costs. Just something to consider. If it's a retrofit, similarly, the existing mechanical room may no longer be necessary, and it might be able to be converted into other valuable uses. In the case of a school, for example, maybe it could be used as a detention room, and certainly that must have some value. Here's a pop quiz. Here's a pop quiz. Basically, is this graph that we're looking at here, does this represent, is this graph represent the long-term fluid temperatures of a cooling dominant or a heating dominant geothermal system? You don't have a clue? If you want to share your answer, feel free to raise your hand or just type it in chat or just unmute your microphone. Okay, so I have no takers, so maybe people are a little shy. Ah, got it. Okay, I got a bunch of takers, and everybody has got it absolutely right. This is a classic example of a cooling dominant system, and so we know that because the temperatures are creeping up because more heat's being dumped into the earth and extracted out. And now the question is this a stable design? Does it warrant some sort of an intervention? And I think we can all look at this, and I'll answer that question and say, certainly, you would not want to install a system where the predicted temperatures are going up like this, yeah. But I actually have to tell you the truth, kind of tricked all of you because we're actually not looking at a geothermal system. What we're looking at are the CO2 emissions in the world as measured in Hawaii over the past 50 years. This is the Keeling curve, and this year we've achieved 400 part per million CO2 concentration in the atmosphere, and predictions are it's going to go up and up and up. So the reason why I show this is to introduce another soft cost, CO2 emissions costs. China is talking about basically taxing CO2 in the next few years. And if they do, it's inevitable that the rest of the world's going to follow suit at some point. When is it going to happen? I don't know. Next year, 5 years from now, who knows? But I think it's inevitable during the lifetime of any geothermal systems that are going to be installed, being installed now. Now the range for these estimate costs range from as low as $20 a ton up to like really high numbers of $600 a ton. Basically, it's anyone's guess at this point. But the point is, you can consider this in a life cycle analysis if you so desire. And the way we do that is basically requires a couple variables. First, we need our CO2 emissions rate. This is the amount of CO2 that's emitted for every kilowatt hour of electricity generated that will be used by that geothermal system. And here we can see the Energy Information Agency, which is sort of a sub-branch of the DOE, I believe, has different states and regions in the U.S., and they have their emissions rates right here. And this is available on websites. And so you put something in here, like for example, this is 0.8. That means for every kilowatt hour of electricity generated, 0.8 pounds of CO2 are being emitted. Then we can put an emissions cost in here. And in this example, I put $100 a ton. If you're going to be doing a 20 or 30 year life cycle cost, you want to put something in that represents what you think the average is going to be over that lifetime. And we have something called the effective initiation delay, which is basically if you think, or your client thinks, yeah, CO2 costs are going to raise things up at some point, but I don't think it's going to be for 4 years. You put a 4 in there, and for the first 4 years of your life cycle analysis, it ignores any sort of cost associated with emissions. So we're almost done with the standard inputs. The last ones are perhaps our favorites, the incentives and tax benefits of geothermal systems. First off, we have tax credits. These can be in the form of fixed tax credits. These can be as a percentage of the cost, upfront cost of installation, and or it can be per square foot. I know a lot of states and regions or cities will have like a per square foot benefit for energy efficiency projects. So you can factor these in here. And we have depreciation. For those of us in the group that haven't studied accounting, which is probably most of us, depreciation always seems like it's something kind of complicated and confusing, but it's actually very straightforward. If you go to Wikipedia and read about it for 5 minutes, you'll say, oh, that's not so bad. These accountants, their work's not that hard. And what we look at is we basically have the option between MACRS, which is Modified Accelerated Cost Recovery System, which is basically a way to get your depreciation money back to you quicker, and it's geared towards energy efficiency projects like geothermal, or straight line, which is kind of the old-fashioned way that takes a lot longer to get your money back. But anyways, for geothermal, we can use MACRS, we can check it, and then the program automatically calculates it, or we can use straight line. Another thing that to consider that I've just sort of popped in here is salvage value. Do we include salvage value in our analysis? You spend $500,000 or $1 million installing a ground loop in the ground. That thing has residual value 10 years in the future, 20 years in the future, 30 years in the future. Do we want to consider that in our life cycle analysis? And then we also have the renewable heat incentive, which I mentioned is basically a credit for renewable BTUs rather than non-renewable BTUs. So finally, let's go over the discount rate in a little more detail, just because it is it's kind of the beating heart of the analysis. So the discount rate is a rate or percentage, like 4% or 3%, that enables us to convert future costs and savings, say in year 5, 6, 7, 8, 9, 10, or whatever, in today's dollars terms. We want to convert everything into today's dollars terms, so we basically normalize everything so we can compare different things. Selecting a discount rate is really, it's a bit of a non-trivial exercise, namely because there are many ways to do it. One approach, perhaps the simplest approach, is to use the average inflation rate in the U.S. over the past century, which is about 3.5%, a little under. Another more technical approach that some financial types prefer is to use something called the weighted average cost of capital for a particular company or institution. This is basically, the WACC is basically how companies value their own time value of their own money. It's basically an opportunity cost issue. Harvard University, where I got that first slide from, at present time uses a 5.5% discount rate when they're doing their life cycle cost analyses on projects. But really, when you're doing this for a client, you might ask them if they have a preferred discount rate. If they have no idea, just choose one. If they do have a preferred one, you can just use theirs. And the take home is the higher your discount rate, the less you value or the more you discount future costs and savings. I know that's a little bit confusing, and it's just these slides will be available as a presentation on the website if you want to go back and look at it, great. Or you can just Google discount rate. There's a million websites dedicated to it. So basically, those are the standard inputs for life cycle analysis. Now we're actually going to take those and sort of use them in an integrated whole and use the GSA module to do some life cycle cost analyses. So I have the program, the Ground Loop Design 2012 program here, and I've kind of done a preparatory loop field design. I'm just going to kind of walk you through it very, very succinctly and briefly so that we're all on the same page. So I imported an hourly loads profile for approximately a 40,000 square foot building. See my cooling peak loads here around 60 ton. My heating peaks are a little bit higher. My annual energy is around here, or my annual hours. I'll go to the monthly loads tab. You can see my total cooling is about 478,000 kBTU for the year. My heating total is about 370. So it's cooling dominant, but not excessively so. It's a reasonably balanced system, although not perfectly balanced. You can graph the loads data and kind of get a sense of it that way. Chosen a heat pump, sort of a pretty modern, mid-sized, 4 or 5 ton, pretty high efficiency heat pump. I designed my loop field. What I chose is, I've chosen, well, I've already optimized it basically, but I have 50 boreholes, 10 by 5 grid with 20-foot spacing. And I'm just going to run a monthly simulation. In this example, I'm just going to go and take these monthly loads here and sort of plug and chug them through this design. The output results are going to be my predicted temperatures in my loop field and then my performance in my mechanical equipment. So I'm going to hit calculate, do a 20-year simulation. Okay, so it's telling me my predicted inlet temperature for cooling is 83, which is very moderate. Gives me a high performance. My predicted EER is 18.4, kind of on my worst day of the year. And my average seasonal performance is predicted to be 20.6, and this is the number we're going to want to use for our life cycle cost because it's our average. On the heating side, my temperatures are relatively moderate, and I have pretty good COP values. Now, in the real world, maybe I'd want to, make this a little bit shorter, save some upfront costs, and then, get little higher temperatures or lower temperatures and lower performance. But I'm just going to leave it as is. So this is my design. I'm working on a project, and I say I want to do a life cycle cost analysis on this using the GSA module. How do I do it? The first thing I do is I open the GSA module here, Geothermal System Analyzer module. And currently there's nothing in here. I'm going to import this project, and it's going to import all the germane variables that related to the design into the analysis. So I hit this button here, Import. And it says, which project do I want to import? I only have one project open right now, so I look at it, life cycle example, and I hit OK. And it brings all this information in. Gives me a bunch of results. But before we spend any time looking at the results, let's go through the design and tab by tab and see what our assumptions are. So we can start over here with our geothermal tab. So the first thing it brings in is the length of drilling. We're drilling 15,200 feet. It brings that in so we can calculate the cost of that. Brings in my cooling loads, which we can see here, 633 hours, 457 hours for heating. See, these are right here. Brings in my peaks, 755 and 810. That information alone gives me my total cooling load and my total heating load. What it brings in then is my average calculated performance efficiencies, 20.6 and 4.4. This is really where you want to have an advanced simulation engine because it enables you to predict the average efficiencies as opposed to just using like a static worst case scenario analysis that less detailed simulations can only provide. We do have pump circulation power basically. I sort of size the circulation pump for the system, assuming a very high efficiency design. I think it's like a 3 horsepower system, just as an example. And then in terms of additional power, I'm going to ignore it, leave it blank. And then mechanical room installation. Let's say that this was a new school, as an example. I said it was a 40,000 square foot office building. Okay, let's leave it at that. Let's say the geothermal system, we're thinking of having heat pumps on each floor, for example. So maybe the mechanical room area total would be 500 square feet. That's yes. So we put 500 in there. We do not have a hybrid design, so I'm going to ignore the hybrid component. When we imported this in and changed all this, we have some numbers that come up here. It shows me my predicted kilowatt hour consumption for my cooling side of my geothermal system and my heating side and my totals. There's no hybrid power, so that's zeroed out. I have my total annual power here. There's no water being consumed, and there's nothing else being consumed because we haven't added anything else in. Other things would be things such as therms of natural gas, tons of coal, et cetera, et cetera. We can go to the conventional tab. This is really where we can define a conventional system that we want to compare. We do this quite quickly. So I could choose, first off, we have to see that our loads are the same, so it's an apples to apples. We see our annual hours are the same here. Our peaks are the same. So the total load being covered by the geo system, the conventional system are the same. I can choose 2 types of conventional systems. I'll choose an electric air-cooled chiller, for example. I'll just choose a natural gas boiler. There's a range of options. What we put in here is our predicted average efficiency of that system. So maybe the average efficiency of the air-cooled chiller is 13. Maybe the boiler is, I don't know, 80%, for example. Sort of nothing special. We could put extra power, and if we wanted, I'm not going to worry about that. We can put the mechanical installation area. Let's say this conventional equipment has a larger mechanical room footprint. Let's say it's a total of 800 square feet for the conventional mechanical room. So we put 500 feet in for the geothermal one and 800 for the conventional, 400 plus 400, for example. Once we do all this, we get some numbers that come up here. So the cooling power is predicted to be about 37,000 kilowatt hours for the year. No water again. And then other, it's going to use about 4,500 therms per year from the boiler. So it does all these calculations for us. And then we go to the Utilities tab, and we can enter our utility rates for the project or location. And I'm just going to leave them as is. So there's a bunch of default values that are in here. You can see electricity is 11 cents per kilowatt hour. Natural gas is $1.25 a therm. These are, relatively reasonable for now. And then the inflation rates is where we put our inflation rates in. Now, I put electricity inflation as about 5%. I'll put it at about 5% per year. And then for natural gas, I'll put it at, let's say, I'll put it at, I don't know, over the long term. I know right now we have a lot of cheap gas, but if they start exporting this stuff internationally, gas prices are going to go back up. I'll put it at like, I don't know, I'll put it at 5.2%. Just, it's just basically our best educated guess as to what these inflation rates are going to be. Maintenance inflation rates, what are the costs of maintenance going to be increasing over time? Let's say it's like, let's just say 4%. And the overall discount rate, inflation rate, this is that sort of beating heart variable in the overall design. So let's use Harvard's rate, for example. Let's say it's 5.4% as an example. I know Stanford University on the West Coast currently is using something a little bit lower because I was just comparing those two. They published all that information. But let's just go with 5.4%, for example. Now, other costs are other things that we can consider in our life cycle analysis. We have a CO2 emissions. So I'm going to leave this at a 1.0. This is sort of an intermediate index clean electricity. If you have a coal-fired power plant that's generating all your electricity, the CO2 emissions are closer to 2 pounds for each kilowatt hour generated. If you're using a lot of hydro, very clean nuclear, et cetera, this could be as low as like theoretically 0. So 1's kind of a middle ground. So I'll leave it at 1 pound per kilowatt hour. If you have no idea where this number comes from, you can hit this little question mark here in the program, and then you can go here to this link, and then it's going to give you these data, like for just different places. Like you can see, like a place like in the West, like Washington State, which is a lot of hydro. Its emissions rate's very low, 0.25, because it's basically a lot of hydro. And a place like New Mexico, where there's a lot of coal, well, hopefully, well, 2. Eventually, they're going to have a lot more solar, I think. If you go to a place like North Dakota, you're going to see it's pretty high too, 2.24. It just depends on the energy mix used for generating the electricity. We can put our emissions cost in over the long term. I'm just going to put my number in as $50 per ton. That's my guess. And also, I don't think it's going to happen for 4 years. Now, really, if it does happen in 4 years, I don't think it's going to start at $50 per ton. But I think over time it's going to increase. I think the average would be $50 per ton. The building's 40,000 square feet. The construction costs are approximately $160 per square foot. What's the lease value of the space? Let's say it's maybe it's $5 per square foot per year. It just depends. Is it an urban environment, suburban, rural? So you can see there's a lot of things. To do this with the highest degree of accuracy, there's a lot of things you need to know. On the other hand, if there's things you don't know and you don't want to know or you don't care about them, you can just ignore them and it'll ignore it in the analysis. Here we get to our system-related costs. We have a subsurface component where we put our cost per unit length in here. And this can vary depending on where you are in the U.S. or in the world. It could be in China, it's $4 per foot. In the South, maybe it's $12 per foot. In California, it's $25 per foot. But I'll put it in as I'll just put it in as $16 per vertical foot. This is if you're doing horizontal systems, you can actually do a cost per square foot of area. And I'm not going to worry about that today. And we have our equipment tab, but there's a lot of stuff we can control here. The database is pre-populated with some information, but we can change it as necessary. We have our geothermal electric heat pump. What's the installation cost per square foot for the conditioned space? I put it at 13 bucks. What are the controls costs for this design? We're going to assume it's a relatively simple design, or sort of, well, somewhere in between, so it's $1 per square foot. Our maintenance costs, we have at 10 cents per square foot per year. And our replacement time, geothermal heat pumps supposedly have an average life expectancy of the low 20s. That's 20. Now I can go to my conventional system I'm comparing against. We had air-cooled chiller electric. I have an installation cost here. Let's say it's about $6 per square foot. Predicted controls costs, maintenance costs, replacement time frame. Natural gas boiler was the other option. You can see my different variables I input here. Again, it comes with a pre-populated database with some general guidelines, but everything's customizable. Then we go to the Incentives tab. And here we can put in our tax incentives. We have an investment tax credit, for example. I know in residential systems it's 30%. On commercial, I believe it's 10%, so we'll put it 10%. If you have other additional incentives in place, like, the city of Chicago gives you a pretty decent incentive for every square foot of space that's being conditioned by a high-efficiency system, you can just sort of, quote-unquote, tweak this number a bit to represent that. It's pretty flexible. Then we have our depreciation schedule. Now, the corporate tax rate, so if your client's a corporate customer, the highest marginal tax rate is 35%. So that's what they want to be claiming for their basically depreciation. If there's any bonus depreciation, you can put that in here. A couple of years ago, it was 100%, then it's dropped to 50%. It's going to drop to 0. So we'll just leave it at 50% for this example. For the geothermal system, we can define the depreciation schedule. MACRS, which is that accelerated schedule, which is basically very beneficial. Also, I'd recommend if you are designing a system in a location where it's offered, just leave that on. If you don't have that, but there's other incentives, you can switch that off. You can define the straight line depreciation for a geothermal system. And then we have our conventional depreciation schedule. Conventional HVAC equipment has a 39-year straight line depreciation. We've listed that there. You can choose your salvage value, whether to include it in the calculation. Again, the main benefit of that really is if you've installed a $1 million loop field 20 years in the future, what's the value of that loop field in the ground? This is a way for you to estimate that. It does have a significant impact on the life cycle analysis. And then the renewable heat incentive. Currently, whatever costs cents per every kBTU that you basically generate from the ground rather than from fossil fuels. So those are all the inputs. Then you go to the Results tab, you hit Calculate. Let's take a look at the results, see what we got. So we have, again, on our Life Cycle tab, we have our variable costs and our fixed costs. And so we have energy. This is the predicted net present value of 20 years of electricity for the heat pumps and the circ pumps. This is the predicted energy for electricity and natural gas over 20 years for the conventional system. We have our predicted CO2 emissions costs in terms of $50 per ton. And again, this starts like at year 5, so the first 4 years are being ignored. We change some of the inputs, you'll see the results change. No water being consumed. We're assuming these are both, say, closed loop systems for this example. Maintenance costs are about halved. My mechanical room lease value, remember we said the geothermal system is going to have about 500 square feet of space being built or consumed. Conventional is having 800. So what's the value of that? And then we put that at about $31,000 cost for the geothermal space and about $50,000 for the conventional space. So you're saving on this line about $20,000 for the geo system. Then we have our fixed costs. They're saying that it's about $250,000 to install this loop field. And again, that comes from 15,200 feet times 16 bucks a foot. Mechanical equipment's about a little over $500,000 for both conventional and geo. Controls costs are here. We have our tax credits. Again, it's in parentheses because it's a minus, meaning it's being subtracted out from the overall cost equation. We have our value of depreciation, and then equipment replacement 0 for geothermal, because we're only modeling for 20 years right now. And geothermal is listed as having a 23-year life expectancy. However, the conventional system has a little shorter life expectancy, so these costs have come in. And again, it's factoring in for the fact that this equipment's going to be replaced in the future, and what's the cost of that equipment predicted to be in the future, and what the maintenance costs, et cetera, inflation rates. Salvage value is zeroed out because we ignored that. And the net result is the net present value, so is over 20 years, the geothermal system all told, it's going to cost about $735,000 to install and operate. All costs, all benefits. The conventional system is going to cost about $1.1 million. So it's about savings of about $400,000 in your client's pocket today, in today's dollar terms, for going geothermal in this example. We can go to the analysis tab. We see, like, over a single year, what are the variable costs. So the energy for the geothermal system is about $6,000 per year, and the conventional is closer to $10,000. The CO2 emissions, in terms of dollars, for geo and conventional, maintenance, and mechanical room lease. And you can just see, like, a 1-year result is going to be. Then we can go to our analysis tab and just kind of look at the different variables. We have our annual savings, our net present value savings, our annual CO2 reduction, which is about 20 tons of CO2, and then over 20 years, about 400 tons. The simple payback here turns out to be 0. The incentives are so good. But if we take the incentives out, that changed quite a bit. The IRR is listed at 2.1%. The IRR is internal rate of return. It's a very fickle calculation, it turns out. And it's like, sometimes it can't be calculated because the numbers can't converge, and sometimes it can. We have our renewable heat incentive values here. And so that's basically, you can graph the data out here and kind of look at things. There's a bunch of reports. But that's basically how you can use this tool to do a quick life cycle cost analysis. What I do is, when I'm doing this, I just have my general inputs pre-populated. Like, I know what these are going to be. I know what my costs typically are. And then what I do is I just import my design and then, change a couple variables to calculate. Then I'm done. And I'll just give you a couple examples. Let's say that you thought the CO2 emissions cost, you think it's a bunk. You don't want to include that, so you just put a 0 in there. And then watch what happens to my analysis. My CO2 cost will go to 0, and this will change as well. So this changes. So you can see how quick and easy it is to just make a bunch of assumptions. Or you could say, oh, my subsurface cost, it went up $2, it's $18. What happens to my overall analysis? Well, it redoes the subsurface costs, it redoes your tax credits, your depreciation, everything's redone. What if I want to go out 30 years? My client says I want a 30-year analysis. Oh, look at that. That's what happens. What if I want a 5-year analysis? What happens there? You can just do different kinds of things like this very quickly and play around with it. What if I think my discount rate's wrong? What if it's 4.5%? Go back, do it again, see how everything's affected different sorts of ways. Another thing you can do is really kind of cool. Kind of when you're designing a geothermal system, it's always the trade-off between how much does it cost to install, how much does it cost to operate over many years. So you could say, like, this particular design, I'm getting a very decent performance here. What if I say, okay, I want to save some money on drilling. I'll sacrifice some performance, and let's do the analysis. So first I'm going to bring this back to 20 years. So here's our baseline here. So I'm going to cut this length to 250 feet. So I'm going to cut off about 17% of loop, see what happens. So let's say it happens with these temperatures here. So these drop up. It's closer to 90. My performance dropped. My original design, my performance was didn't change too much, actually. Interesting, it didn't change much at all for this particular design. But I've saved some drilling lengths in this example. So I'm going to import this design now and redo the calculations to see what would happen financially if I change the system a bit. The key variable here is, let's just look at these life cycle cost totals and just see what happens to these numbers. Or we can look at the analysis. The total net present value savings is $394. So I'm going to import the new design. So my net present value savings increased to $421. So taking the, slightly increased operational costs, but upfront capital savings into account, I've just saved $30,000 additionally net present value right there, just by playing with that design there a little bit. That's how you can use the tool in kind of an iterative, integrated approach to, help you fine-tune your designs and your cost-benefit trade-offs. So the official presentation's done now. So I'm going to open this up to anyone who has any questions. If you have any questions, you can chat them in, you can unmute your mic and ask them, or you can just raise your hand and I'll unmute your mic. So feel free to ask away. Give you a few seconds to formulate your thoughts. Okay, it looks like we are question-free. I'll just wait another minute to make sure no one has any questions. And while I'm waiting, I'll just make one announcement just as a reminder. We have a whole series of these classes scheduled for the rest of the year, typically the last Friday of every month. We have a range of industry experts coming in to provide these classes. I think they're going to be really interesting because we're really looking at the different sort of problems that geothermal faces. We're trying to address them, communication issues, energy modeling, et cetera, et cetera. So please join us if you're interested. And also remember, if you want more detailed classes, we offer much more detailed classes. This is kind of an introduction that span in time from 3 hours to like 20 hours. And then also for anyone in the class, if you have software, if you're already currently our customer, we're very happy to have you using the software. If you're considering, we'd happy to have you as a customer as well. And for participants in the class, for a short period of time, we're offering the software upgrades at a discount. Yes, I've been asked to show the future upcoming courses, just as a refresher. And this is just a list of the future classes. So next month, effective energy modeling with an expert in energy modeling, and then thermal response testing, how to communicate between engineers and drillers to minimize miscommunication and problems, geothermal technologies and climate change, and then how to educate geothermal operators so that when they actually get the system in their hands, what do you tell them to make sure that they use them properly? So we have a question. Great, thank you for the question. So basically the question is, when is it appropriate to use mechanical room lease rates? So let's go back to this. We have this variable here called lease value. And we've defined this at $5 per square foot per ton. And the way, when that would be useful would be essentially if it's a retrofit. So let's say we're using a school. Let's say it's a school and the central plant is 1,000 square feet. And they're going to say, okay, I want a geothermal system. It's going to be distributed. The heat pumps are going to be each classroom. And we don't need that mechanical room anymore. So suddenly they say, what are we going to do with this mechanical room? Oh, we can turn it into storage. What do we think the value of that storage is going to be? That's when you put the lease value in there. You put like $1 in there if you think the storage is not worth very much. They're going to turn it into like a treat. They're going to put some windows in there, make it an indoor, who knows, art center. They say, oh, that's going to be worth $3 per square foot. That's when you put that in there to kind of figure out what the value of that space is. So in a retrofit primarily. Any other questions about anything? Okay. So basically, we have another question. Where can we find today's slides online? So after the presentation's done, in the next day or two, we're going to format it. We're going to upload it onto the internet as a video. And I believe Jeff is going to be sending out an email out, letting people know that it's available. So you could just go to the Ground Loop Design site, and then there's a link to like webinars. But we'll be sending out an email that says where those are. It's a good question. It's a good question. If you're really bored to death, Eric, and having trouble falling asleep, you can watch it again. Yeah. So another question: how and where depreciation is calculated? Okay. Yeah. Depreciation is certainly, if you're new to life cycle cost analysis, it seems like something just very foreign. But if you, again, as a preview, go to Wikipedia and just read about it, and you're going to think, oh, this makes sense. It really isn't too bad. So basically, depreciation happens here. What depreciation is, first off, is the following. You buy a capital good. You buy something, for a company, and the IRS allows you to depreciate it at a certain rate. If it's a conventional mechanical system, not high efficiency, they say you can depreciate it over 39 years straight line, which means every single year you take 1/39 of the value. So for example, let's say that you bought a conventional mechanical system and it cost you $39,000. Straight line depreciation for conventional is 39. And so basically, so if you divide 39,000 divided by 39 years, it's $1,000 per year. The IRS allows you to basically depreciate $1,000 per year. So in year one, you depreciate it by $1,000, and then you multiply that typically by your tax rate. In this case, say 35%. So it's 1,000 times 35% is $350. So you're going to get about $350 worth of tax credit for the depreciation your first year for that project. The second year, it's another $1,000. You multiply by 0.35, and it's $350 again. But it's not quite $350 because the future value of money is a little different from the present value. It's actually worth a little less. And by the time you've gotten to year 39, it's still $1,000. But $1,000 39 years from now is going to be worth like nothing. It'll be worth like 200 bucks. So basically, you don't really get as much out with a long-term depreciation. When you have an accelerated depreciation, like 5 years or 10 years, you know, you're depreciating the whole system over a much shorter time frame, so the value of each year is higher. And 10 years out, the time value of money is still worth more, so you get a big benefit. Now, geothermal, modified accelerated, this I believe is like a 7-year depreciation, 6 or 7, and it's accelerated. It's not even. It's not, you know, like the first year you save 15%, the second year it's 25%. It's just sort of this curve for depreciation. And really, it saves you a lot of money. And let's take a look to see what that actually means. So this particular design, just, you know, the installation cost is $600,000 plus $225 plus $40. This is your total installation cost. So it's somewhere around $850, say. My depreciation over 20 years is $276,000. Now, if I go off of Geo and I switch to a straight line conventional schedule, like this is like the conventional depreciation, 39 years. Let's see what we lose from the depreciation bonus. Currently, we're saving $276, but if I switch to 39, it drops to $193. So we're losing about $80,000 in value by doing straight lines. So you can see what the geothermal accelerated schedule provides for you, as an example. Or I could do like a straight line 10-year. And what's the value of a straight line 10-year for my geothermal depreciation? It goes from 193 to 262. So you see it's 262. If I go back to the best one, Mackers, it brings it up to 276. So you can kind of see how that plays out. Now, Micah, did that answer your question? Does that help? If you want a further explanation, I'm happy to provide it. Okay, great. Yeah, it's interesting how people develop these concepts of depreciation. We had another question. The question is the previous webinar online now? He was unable to participate. Yes, it is. It is online on the website. And again, Jeff will be sending an email out that shows you where that one is. The first one was on headering design optimization for piping systems and purging. Any other questions about anything that I can help with? No? Okay, thanks. Well, it looks like we're all done here. Thanks for all your participation today. Thanks for joining us, and thanks for being customers. We're really happy to have you as our customer. Another question. Great. If we create another alternate, can you re-import the same design but with a slight difference, different length? Yes, you can do that. Wait, question, Adam. What do you mean by alternate? Do you mean a different conventional system? Is that what you mean? Okay, got it. Yeah, Mike. No, Adam, no problem. Just so, what do you mean by alternate in that question? I think you mean alternate design here, right? So I'm going to assume, Adam, that you mean that if you change your loop field design here, can you re-import it to compare? Yes, you can, and I'll show you again how to do that. Right now, my design is 250 feet long, 250 feet deep per borehole. I say, what happens if it's 280 feet? Well, I'll do an extreme example. Let's say it's 400 feet. I'll do an extreme example to illustrate a point. So if it's 400 foot deep boreholes, what happens to my performance of my loop fields? I got it. Now I understand the question. Okay, well, I'm going to answer this question that you didn't ask first, then I'll answer your question. You saw when I really bumped up the length to 400 feet, my performance really, my temperatures are much more moderate, much higher performance, but my length has gotten a lot longer. So if I import this design, my installation costs are going to go up, my energy costs are going to go down, but the net's going to be a loss, I think. So yeah, basically, I just lost $100,000 in lifetime value on this particular design based on this configuration. But Adam's question was a little different. There's an alternate button in the GSA at the top right. What's its function? Okay, good question. So on the conventional tab, we can define multiple different conventional systems. So for example, system 1 here is an air-cooled chiller, electric, and boiler, natural gas. I could define a system 2. Like I can make it a very high efficiency air-cooled chiller. I could make it a very high efficiency natural gas boiler. And then I could basically have my mechanical room area here. Now if I did this, I'd want to change my costs. because these high efficiency systems probably have a higher cost per square foot, so the installation costs are going to go up. But I'm not going to worry about that right now. I've just defined a second system. When I go to my results here, I can basically see my simulation results for my first design and for my second design, see the difference. So with this high efficiency system, you see my energy costs are a bit lower. I'm saving about $25,000 a year in energy costs. Then you see over the life cycle, I'm saving about $30,000 right there. And so you can kind of just analyze different scenarios against the geothermal system, and that's the function. You can have up to 5 alternates that you compare at one time to your geothermal system. Make sense? Does that answer your question, Adam? Great, great. Any other questions? Anything at all? No, okay, well, if you do have any additional questions, feel free to contact us. We're available. We have tech support Monday through Friday. And thanks again to everyone for participating. I hope you've found this webinar to be valuable and informative.